Lesson 9.6, Exponential Growth and Decay. Here are some general formulas that we can use for exponential growth and decay. They look very, very similar. However, in the growth formula, we're going to take in parentheses 1 plus r, our rate, and in the decay formula, we're going to take 1 minus r. So in this formula here, a represents the initial amount, r is the rate. A lot of times they give you the rate as a percent, but you need to change it into a decimal. And then t is the time, typically in years, but it really could be in weeks or whatever the time frame is. And then of course, y is the amount left. If it's decay, y should be smaller than what you started with. And if it's growth, y should be bigger than what you started with. Okay, so in 1910, the population of a city was 120,000. Since then, the population has increased by 1.5% per year. If the population continues to grow at this rate, what will the population be in 2010? As you read through the examples, you want to look for some clue words that will tell you if it's growth or decay. The clue word in this one is it continues to grow, or here's another one, the population has increased. So we're going to use the growth formula. Y equals A times 1 plus R to the power of T. So let's fill in what we know. The population of a city was 120,000. That's your initial amount, A. In parentheses, we've got 1 plus r. The rate of increase here is 1.5%. So as a decimal, that's 0.015. And t is our time in years. We also know that value. From 1910 to 2010, that's 100 years. If you subtract those dates, we get 100 years. And the question is, what will the population be in 2010? 100 years later, basically. So we're trying to figure out what y is. Now, this you can type in on your calculator. If you want to, you can type in 120,000 times 1.015 if you add those two numbers together, and then hit the power of 100. You should end up with 531,845. So if the rate of growth continues to be 1.5% in 2010, this city will have a population of 531,845. Example 2, a cup of coffee contains 130 milligrams of caffeine. If caffeine is eliminated from the body at a rate of 11% per hour, how long will it take for half of this caffeine to be eliminated? Okay, so again, as you read, you need to decide, is this an example of growth or decay? Because we're talking about caffeine being eliminated from the body, this is decay. The caffeine is going away. So let's use the decay formula. Y equals A times 1 minus R to the power of T. And let's fill in what we know. We know that the cup contains 130 milligrams originally, so that's our initial amount, A. Now in parentheses, we have 1 minus the rate, and the rate here is 11%, so that's 0.11. T is what we don't know. The question is, how long will it take? T is what we're trying to figure out. And the question is, how long will it take for half of this caffeine to be eliminated? So at the end here of time t, whatever it is, we're going to have half of the milligrams left, and half of 130 is 65. So y, the amount left, is 65. So I need to solve this equation for t. Well, it's just an exponential equation. So let's use what we know about logs here to solve this. First thing I'm going to do is simplify what I have in parentheses. So I have 65 equals 130 times 0.89 to the power of t. Now I'm going to divide each side by 130. And I get 0.5 equals 0.89 to the power of t. Now I can take the log of each side here to figure out what t is. If I take the log of each side, then remember I can bring t out in front, bring the power out in front. So this is what I have. Log of 0.5 equals t times log of 0.89. I'm bringing the power in front of the log using the power rule. It's the property number 3 that we talked about a couple of days ago. Okay, now all I need to do is divide by log of 0.89. So it's the log of 0.5 divided by the log of 0.89, and that will give me t. As I calculate this here, I get 5.9480. And so we could say that it takes about 6 hours for half of the caffeine to be eliminated from our body. About 6 hours. So another model for exponential growth and decay using base E is actually preferred by scientists. A lot of times the scientists will solve radioactive decay problems, a fossil decaying in the ground or whatever it happens to be. So these models are just another option that we have using the base E. In these formulas, you have y equals a times e to the power of kt. That's your growth formula. The difference in the decay formula here is you've got a negative k in your power. A times e to the negative kt power. A is the initial amount again. T is the time. K is some constant. Any number could be k. Example 3. As of 2005, China was the world's most populous country with an estimated population of 1.31 billion people. The second most populous country was India with 1.08 billion. The populations of India and China can be modeled by I of t equals 1.08 e to the power of 0.0103 t, and C of t equals 1.31 times e to the power of 0.0038 t. So we're using the function I of t for India and C of t for China. According to these models, when will India's population be more than China's? So these growth formulas here are written using that second model with the base E. The question is, when will India be bigger than China? So what we really need to solve is I of t is greater than C of t. And of course, we're going to solve for t, figure out how many years will it take for India's population to be larger than China's. So here's what I want to set up. 1.08 e to the 0.0103 t is greater than 1.31 e to the 0.0038 t power. All right, so I've got the formula or the inequality set up here. Now I want to get rid of the t's and the powers. So how do I do that? Well, I'm going to take the ln of each side. Take the ln of each side because the ln is the inverse of e. Now we're going to use the property of logarithms here. I've got a product of a log, a product behind the log here, so I can split it up into two logs using a sum. So it's the same thing as ln of 1.08 plus the ln of e to the 0.0103 t power. Now, I want you to think about how that's helpful to me. How can I eliminate e now that I've got those split up? So because I've got a product here in the log, I can split it into the sum of two logs. And I can do the same thing on the right side of my inequality. I can rewrite this as the ln of 1.31 plus the second factor here is ln of e to the 0.0038 t power. So these are your two factors, 1.31 times e to the power of this. So again, split it up using the sum of two logs. Now we know that the ln and e are inverse operations here, so they actually cancel each other out, and I get the ln of 1.08 plus, I'm left with this power, 0.0103 t. And that's greater than the ln of 1.31 plus, again over here the ln and e will undo each other, and you get 0.0038 t. So that's helpful because now I don't have a base e anymore and I can solve for t. So let's get t on the same side here. I'm going to subtract 0.0038 t from each side. So the ln of 1.08 plus 0.0065 t is greater than the ln of 1.31. Now let's keep going here to try to get t by itself. I'm going to subtract the ln of 1.08 on each side minus ln of 1.08. And then my last step, I'm running out of room here, so I'm going to kind of squeeze it in. My last step, to get t by itself, I need to divide that by 0.0065. So this entire thing divided by 0.0065. Now when you type this in on your calculator, make sure that you've got a parenthesis in front and behind your numerator here so that your calculator knows that this is the numerator of your fraction, and then you're dividing by 0.0065. You should get t is greater than 29.7, approximately, I think. Okay, so now what this means is in about 30 years, India's population will be more than China's. You can either say in 30 years or you can say the year. When will that happen? So 30 years after 2005, it's going to be about 2035. So my answer here, I'm just going to say in the year 2035. Always make sure that you're answering the question that's being asked. According to these models, when will India's population be more than China's? Well, we got t is greater than 29.7, so that's about 30 years later. And so we got to say it's in the year 2035. Okay, I'm going to show you one more example, kind of giving you a variety of examples here. So here's the last one. It's a radioactive decay problem. The half-life of a radioactive substance is the time it takes for half of the atoms of the substance to disintegrate. All life on Earth contains carbon-14, which decays continuously at a fixed rate. The half-life of carbon-14 is 5,760 years. That is, every 5,760 years, half of the mass of carbon-14 decays away. What is the value of K and the equation of decay for carbon-14? So we're looking for an equation this time. Here's what we have so far. We don't know the initial amount of carbon-14. We kind of want a general equation for any amount of carbon-14, but we do know that the half-life is 5,760 years. And I want you to use the second model for growth here. So y equals a times e, or I'm sorry, for decay, to the negative kt. This is the formula that we're going to use this time. This one is typically used for decay, radioactive decay problems. Okay, so we don't know what A is, but I know that the amount at the end is going to be half of it because we're talking about the half-life. So Y, the amount at the end of all this is going to be half of A. So I'm just going to say 0.5 A equals A times base E. We don't know what our constant K is, but I know that the half-life, the time in years, is 5,760. And so this is all I can really fill into the formula. Take a look at what I did here. A is the initial amount, and on the other side of the equal sign, I'm going to have half of A, so 0.5A. Now I can divide each side by A. A divided by A is out. A divided by A is out. And now I have 0.5 equals E. I'm going to also rewrite this power so that the number's first and the letters second. Negative 5,760 times K. What I need to figure out what K is. That's our constant in this equation. So I want to figure out what K is. I need to take the ln of each side to cancel out the E. Okay, so ln of 0.5 and the ln of E. ln of E, we know we get negative 5,760K. And the ln of 0.5, we're going to calculate in a minute here. Now let's divide each side by negative 5,760. And we get our constant. K equals, pretty small number, 0.00012. Okay, so what is the value of K? Here's part of your answer, 0.00012. And the other question is, what's the equation of decay? So now I need to write the general equation for carbon-14, the half-life of carbon-14. Here it is. You want to say y equals A times E to the negative 0.00012 t. Now what I can do with this formula is plug in any initial amount of carbon-14 and maybe the number of years, and then figure out what I'm going to have left. All right, there we go. I've got one more here for you to try on your own. Use the first decay formula here when you set it up, and we'll see if you get it right.